The topic today is fatigue under combined loading. We have seen uh, fatigue under bending, axial loading, and torsion if they occur in isolation. What if they are combined in one problem? For example, bending and axial, or bending plus torsion, or all three of them. So there are some things that need to be taken care of when we encounter such a problem. The first of the problems is the marine factor KB, size factor KB. If you recall from the previous lessons, uh, equation 620, according to equation 620, KB is equal to D over 7.62 power minus 0.107 for D between 2.79 and 51 millimeters, and the value for this KB becomes 1.51 D power minus 0.157 for D greater than 51 millimeters. Now these values are for bending, and incidentally they are the same as well as for torsional problems. The value for KB can be taken from this. But when it comes to axial loading, as one can see from equation 621, KB is taken to be 1. So the first problem that we encounter is this. If we are experiencing bending, axial, torsion all at the same time, which of these values should be taken? So this is our problem number 1. Problem number 2 concerns the next marine factor, that is the load factor, Kc this time. Now Kc again, if you refer to equation 626, the value of Kc recommended is 1 for bending, 0.85 for axial loading, and 0.59 for torsion. Now again we have to consider, if we have this loading in combination, which one of these should be. You cannot use all three. So this is again something that we need to consider here. The next problem that we have to deal with is that of stress. Now here we have more than one type of stress involved. The third problem is you have normal stress because of bending, you have normal stress because of axial loading, and then you have shear stress as a result of torsion. Now for all of these, even for the same geometry, you will also have fatigue stress concentration factor for bending, fatigue stress concentration factor for axial loading, and fatigue stress concentration factor for torsion. And even for the same geometry, you will have different values, because these values are different for the different kinds of loading. Obviously geometry plays a part, but even if you have the same geometry and you have different kinds of loading, then your factors of safety will be different. Technically speaking, Kf is achieved after consulting Kt, the geometric stress concentration factor, from the relevant appendix, and then applying a notch sensitivity, and then you get the value. So you have three different kinds of values, and if it's a fluctuating case, then your the complexity increases even more, because now you have not only these three types of stresses, but also potentially you have the amplitude component of bending stress, the amplitude component of axial stress, and the amplitude component of torsional stress. And you also have the mid-range component of bending stress, the mid-range component of axial stress, and the mid-range component for torsional stress. Now, with so many stress values, how to compare with your strength values? Because ultimately we have this you compare these values with the ultimate tensile strength, or and your endurance limit, or your yield strength, etc. So you always have some stress values and then you compare them with these strength values, but here you have many such values. How to compare them? This is a problem. So how we deal with this kind of a problem is this. What we do with the first of our problems is we simply take KB for bending. We don't take it for axial. Even if axial loading is there, torsional loading is there, you take it for bending, and for bending and torsion is the same. So we are going to stick to this as if it's simply bending, and incidentally it is the same for torsion. So we take this. So this is our solution for the first problem. We are going to, obviously we are going to deal with the axial thing later on, but as far as KB is concerned, we are going to use KB for bending as if there is no axial loading there. And I'm again repeating that KB for bending is the same as KB for torsion, because this equation 620 is for both of them. Now, before coming to problem number 2, I would like to talk about our problem number 3. What we do about this is, because we have different stress concentration factors, we apply each stress concentration factor to each type of loading. If you have 3 types of loadings, you will have 3 types of stress concentration factor, and then we, using these stress concentration factors, we calculate these potentially 6 quantities. But how to compare these with these? Because let me remind you that you have the fatigue failure criterion, for example, modified Goodman, that involves so these are the material properties, and here you are supposed to apply the stress quantities, but here you have so many stress quantities. So how to utilize this kind of an expression when you have so many quantities? What we do is we apply the von Mises theory and calculate distortion, which is also called distortion energy, and calculate the von Mises stress for the amplitude component and the von Mises stress for the mid-range component. The von Mises stresses. Once you have these stresses, so what we do is these give rise to this, and these give you this value. So once you have these values, you can just compare these values with, you can put these values here and here, and then calculate your fatigue factor of safety. Now, one thing that I didn't cover is this. What about you have the axial loading there, but for KB you just ignored it. You use the value for bending and torsion. So what about this one? This is a problem. Similarly, you have in KC, you are using the value of Kc is equal to 1 for bending, because we cannot apply Kc 3 Kcs. If you have 3 types of loading, you can only apply one. So we are going to apply this Kc for bending, which is, so what about this and this? You ignore this one, you ignore these. So what we do is we have to modify these values, the one measures values, so that we have reflected these things there. So the solution for this problem is, when we calculate to include the effect of this axial loading, this load factor Kc 0.85, what we do is, when we calculate the amplitude component of axial stress, we divide it by 0.85. Now what this does is, recall what 0.85 did. 0.85 was, you decrease the endurance limit. This actually, for your problems where these occur in isolation, 0.85 decreased the endurance limit. Now endurance limit, you cannot decrease the endurance limit just for axial loading. You just have one endurance limit. You cannot decrease it. If you decrease it, then you also have bending and torsion applied. So what we do is, instead of decreasing the SE here, this 0.85, this increases the stress component. So you essentially do the same thing. You, instead of decreasing strength, you increase stress, and because stress can be increased on an individual level for axial loading only. For axial loading also, only the amplitude component, and these things are tried and tested empirically, so there's a sound practical basis behind it. So you increase the stress component, and so the effect of this 0.85 is applied. As far as this 0.59 load factor for torsion is concerned, you don't apply it, because the von Mises stress already, this already accounts for the 0.59 load factor for torsion. When we calculate von Mises stresses, this thing, because recall what this was essentially the difference between, actually this was 0.577, which was the conversion factor for you apply 0.577 to convert your strength to strength and shear. So this was the relationship. So this 0.577 comes from the von Mises theory. So when you calculate this sigma A prime, sigma M prime, you are calculating von Mises stresses. There is no need to apply this factor 0.59. So essentially what we do is, we convert all the stresses, the amplitude components, into one stress quantity, sigma A prime, and the mid-range components, we again combine them to give you one number, sigma M prime. And when we use the axial component, the amplitude component of axial stress, we divide it by 0.85, so that the effect of Kc is applied. And apart from that, we don't apply the number 0.59 anywhere. There's no need for that. And when it comes to the factors, size factor Kb, you take that for loading and torsion, which is the same thing. And as far as Kc is concerned, you take the factor 1, that is for bending. So this is essentially what we do to tackle these problems. So now, once you have these values, what remains is simply this. Instead of using sigma A over SC plus sigma M over SUT is 1 over NF, you basically use this equation. And you calculate the value of NF. And if it's a case of fluctuating load, then you will have a value of this and both values, and you'll apply them here and get this. But if it's a case of fully reversed fluctuating, if it's a case of fully reversed, then sigma m prime will be 0. All your the mid-range components are 0, and all your some of your amplitude components will have values, so you will have this not equal to 0. But all your mid-range components, if they are 0, then it means that your sigma m prime will also be 0. This is a case of fully reversed loading. In that case, obviously this thing becomes 0, so you'll have, or NF is simply the ratio between the endurance limit and the amplitude component of stress. This is how you apply this, and obviously this is the modified Goodman criterion, but the thinking is the same when you use the Gerber and other criterion. For example, you can also use Gerber, ASME, elliptic, etc. in the same way. And once you have calculated the yield, the fatigue factor of safety, this should be followed by, it's a good practice to checking for yield, followed by a yield check as usual. And let me demonstrate the use of these equations in a numerical problem. Let's read this. This is not from your textbook, but it doesn't matter. All these problems are similar in nature. The shaft of the disc sander is made of steel having SUT is given, SY is given. This is a sander. You put an object close to this periphery and then you press it, and because of friction you have this sanding operation, and when you apply this Fn, normal force, there is a tangential force generated, and obviously you have loading on this shaft, and because this is rotating, you'll have torsion as well as bending loads, and we'll see that in detail. The most severe loading occurs when an object is held near the periphery of the disc with sufficient force to develop a friction torque of 12 Nm. This is the torque which approaches the stall torque of the motor. Stall torque is the torque at which the motor will stop. So you're approaching that, you won't stall the motor, but that is the maximum torque generated. Assume a coefficient of friction of 0.6 between the object and the disc. You have this coefficient given. Analyze the shaft for fatigue. We have to analyze the shaft for fatigue. There is if you apply forces here, there is a moment arm 50 mm here and 100 mm here, so there will be stresses here, and you have fillets here, so there will be stress concentration factors here also. The shaft has been machined to size, so your finishing has been given. Now first let's deal with the strength part of the problem, and then when we come to the stress part, we'll have more discussion about the loading. Strength part is as usual, and please note that you have when you apply load here, if you talk about this there'll be compressive load here. If you uh, have a free body diagram, if you cut it here, there will be a compression here, there will be a torsion here, there will be bending, two components of bending, and we'll discuss it. So it's a problem where we have combined loading. So SUT given 900 MPa, SE prime is simply 0.5 SUT is equal to 0.5 into 900 is equal to 450 MPa. Now SE values, Ka, all the factors the same, Kc, Kd, Ke, Kf, Se prime. These will be 1. Temperature, reliability, miscellaneous. No mention of any of these things, so these are all 1. We have to deal with these, and we just discussed how we negotiate with Ka, Kb, and Kc. Ka is simply, we take Ka for that of bending. Ka is the material property. K is surface finish factor. So that is taken as usual. This has been done many times. Table 6.2 for machined surface, you have A is equal to 4.51 and B is equal to minus 0.265. Putting these values here, Ka is equal to 4.51, SUT 900 minus 0.265, and this turns out to be 0.74. This is your first. Now Kb, Kc we just discussed, both Kb and Kc. You take both of them for bending. Kb for bending and torsion is the same thing, and Kc you take 1 for bending. So this will let's do it here. D over 7.62, this is your expression for bending and torsion. We are focusing on bending here. 16, this is the diameter. This is the diameter of the shaft. And this is 0.92. Kc as discussed, 1 bending. We'll apply the factor for axial in calculation of stresses. So your SC then becomes 0.74 into 0.92 into SE prime, which is 450. This is 306.4 MPa. Now this is the strength part. What about the stress part? Things get interesting here. This is relatively simple, but now we have to deal with the combined loading effects. Let's make a free body diagram here and cut it here, because maximum stresses will be on this section. There's a maximum moment arms here, and then you have these fillets, so there will be stress concentration also. The maximum stresses will be here. So let's cut this on this most critical section. So you'll have something like here you have fillet, and let's specify your coordinate axes. What we are actually saying is this is our x-axis, this is our y-axis, This is our z-axis out of the paper. This is what we have drawn here. So we are going to do a 3D vector analysis, because for 3D problems it's better to use the vector equation instead of a scalar equation. So you can have fx, fy, fz, three force components, and you also can have three moment components. You have, this is tx, this is torsional, and this is my, mz. So let's find out what these values are. Some of them might be zero, but let's do a 3D analysis. 3D vector analysis. Again, this is nothing new. This is your statics or mechanics of materials 1 all over again. So the first equation, the fourth equation, fxi plus fyj, these values, plus fzk plus, what are the other forces? Fn in the x direction, ft in the z direction, plus fni plus ftk is equal to 0. You can rewrite it like this: fxi plus fyj plus fzk is equal to minus fni minus ftk. In other words, fx is equal to minus fn, fz is equal to minus ft, and your fy is equal to 0. There is no corresponding j component, so this is 0. So what you have is, you have this value fx, you have fz, this is the normal stress, I'm sorry, this is the normal force, this is the shear force, and there is no shear force in the y direction. These are the, we don't know the numbers yet, but we'll come to that later on. First of all, we have to go to 3D moment equation. The moment equation, similarly, you write all these values, these we need to find out. So txi plus myj plus mzk, this much is these. And what about the other, any other moments? Yes, there are. You have this one point where you have applied forces, so fn and then ft. So you again use a very familiar device, cross product ij, again nothing new, statics all over again. And here r, this is r and this is f vectors, and r is from your point of interest. We need to find, the practice is to find the resultant forces and moments here, and then apply your different bending formula and torsion formula and everything. So this is your point of interest. So you start from here and go to this. So this is minus 50 in the x direction and plus 100 in the z direction. So minus 50 in the x direction, plus 100 in the y direction. Minus 50 and plus 100 in the y direction. This is in the y direction. Z direction would be out of this page, so there's no z value here. So this is 0. And what about the forces? Force, this is positive x, this is positive z. So fn 0 and ft. This turns out again is 0 because it's an equilibrium equation, just like this. So rewriting txi plus myj plus mzk plus ft minus 0 minus j minus 50 ft minus 0 plus k minus 100 fn is equal to 0. This is just, we just open this up, and if we rewrite this equation again, txi plus myj plus mzk is equal to, take it on the other side, minus 100 fti minus, take it on the other side, minus 50 ftj plus 100 f and k. And from this it's very obvious that tx is minus 100 ft, my is minus 50 ft, and mz is 100 fn. These three values we get. So what we have here then is the situation where, let's draw it here again. The situation is something like this. You have this fx value, you have this fz value. As far as stresses are concerned, you have tx, you have my, and you have mz. This is the situation. There is no f. This, let's write it, fx, fz. You have these five components. This fy was 0. So let's find out the values. We have these values, but in terms of the other variables, what do these things become in numerical terms? Let's see. Let's recall these numbers. Tx, we know that the value of Tx, torque. What is the value of torque? Let's go back to the question statement. The maximum value of this is 12 Newton meter, because this is the stall torque of the motor. So when you apply the load, this is the maximum value that can be applied, and you apply very near to that value. So what you do is, we know that Tx then becomes 12 Newton meter. This is the maximum torque. You need to design your system for the maximum torque, and or you can write it as 12,000 Newton millimeter. This is Tx. Now we just calculated the value of Tx minus 100 ft. So in place of Tx, write 100 ft. Minus sign is just it just gives you the direction of that. So when we talk about the magnitude, just put the value of 100 ft, 12,000, which gives you value of ft is equal to 120 newtons. Now this ft we call minus ft for fz. So you know the value of ft, 120, and this was the direction is plus z axis. So actually what happens here is this fz is in the opposite direction to z axis. This is not like this because it is a minus sign. It is actually, this is fz, and the value is equal to ft, which is 120. What about fx? Let's move on. What is the relationship between fx, this fn, sorry, f and ft? You apply this fn force, and because of friction, this ft generates. The relationship is a very familiar one between ft and fn. ft is equal to fn. This is the coefficient of friction, and coefficient of friction has been given as 0.6 for this case. So if you need to have the value of fn, this is simply ft over mu, and then you have this value 120 you just have, and this 0.6, this is 200 newtons. Now recall again fx, the value of fx, is minus fn. Fn is positive x direction, fn positive x direction, so ft opposite side. So you have again fx not like this, but you have this is fx, and the value of fx direction is this one, value is equal to fn, and that is 200 newton. In fact, this is compression. So from these we can write that fx is 200 newton compression. As far as fz is concerned, because this will cause compressive stress, as far as fz is concerned, which is 120 newton, this causes this fz, this is a transverse shear force, so this causes a transverse shear stress fz, this one. But we will neglect this transverse shear causes transverse shear stress, we will ignore this. It may not be a very good idea ignoring it here, because it's a relatively short shaft. For long shafts, long beams, long shafts, you can easily ignore it. This is not a very long shaft, so it may not be a very good idea, but we'll just, for the sake of simplicity, we are going to ignore this. Now we come to the moments, and that is very simple. You have these values my and mz. So my is 50 ft, mz is 100 fm. Just put in the values. Now we can put numbers on these values also. My is equal to 50 ft, mz is equal to 100 fn. Putting the values, ft we know 120, fn we know 200. So this is 6000 newton millimeters. This is 20,000 newton millimeters. Now what is happening here is there is a torque and there are two bending moments. This torque, this causes shear stress. These two cause bending moment, because these are at 90 degrees. Again, let's see here. This causes a bending moment like this, and this causes a bending moment like this. But these are in this same plane, 90 degrees apart. You can have a resultant of the two in this plane. You can have a resultant of the two, because these do the same thing. My, mz, they produce normal stresses. You can add them vectorially, obviously, and you can simply get the value of my square plus mz square. Again, this is nothing new. This is your simple mechanics of materials. 6000 square plus 20,000 square, and this is m turns out to be 20880.6 newton millimeter. Let's take stock of the situation. Again, you have this section. Now we have considerably reduced the complexity of the problem. We have now reached a certain stage where we can sum this up. This is your section. There's a fillet here. You're talking about this centroid, and there is a compressive force of 200 newton. There's also a transverse force here, Fz, but we are going to neglect it because this causes compression, that causes transverse shear. But because we are dealing with torque, as compared to that, we are assuming that the transverse shear will be a small quantity. And then you have a torque here, and the torque is 12,000 newton millimeter. This causes sigma axial. this causes torsion. And then you have in this plane you have a bending moment which causes sigma bending, and the value of this is 20880.6 Newton millimeter. This is the, I've just ignored the transfer shear. You can add that also if you want. So this is the situation as it is. So the next is, obviously we have to apply fatigue stress concentration factors and then calculate these values. So let's refer to appendix A15. You have three types of loadings. So for the three types of loadings, you have three stress concentration factors. You have D over D. If you go to appendix A15, there are figures A15, 7, 8 and 9. One for axial, one for bending, one for torsion. So D over D, 18 over 16. The bigger diameter, 18. The smaller diameter, 16. And also there is an excess of R over D. R over D is this R, 5 over D, 16. 5 over 16, which is 0.3125. So if you look up the value of KT for axial against these, it is nearly equal to 1.35. KT, these are geometric stress concentration factors. We have not included the notch sensitivity yet. KT bending for against these values, because geometry may be the same, but because of loading you will have different stress concentration factors. This is 1.25, and KT torsion, this is 1.1. Now apply, the next step is to apply the notch sensitivity. Notch sensitivity, the next step is to apply notch sensitivity. Figure 620 will come into play, and also figure 621. 620 deals with normal stresses, so it will deal with the axial and bending. This deals with shear stresses. So this will give you the notch sensitivity for torsion. Now you have to, in these figures, you have to read against the value 5 millimeter radius and SUT is equal to 900 MPa. These are the two conditions, and against these, notch sensitivity for bending and axial is the same thing. Normal stress is 0.92 and Q for torsion will be 0.9. Again, these are very rough values, but that will do. These are the, and then if you have the geometric stress concentration values and also have notch sensitivities, next step is simply to calculate the fatigue stress concentration factors, which are nothing but, again, very familiar expressions by now. 1 plus Q KT minus 1. So relative Q's will be 0.92 KT, in this case axial 1.35 minus 1. 1 plus again 0.92, these are the same Q's, 1.25 minus 1. For torsion the Q is different, 0.90, 1.1 minus 1, and if you calculate these you will have 1.3, 1.2 and 1.1. These are the values. These are the stress concentration factors that you are going to actually apply. Now, coming back to this situation, I think you have torsional stress, you have a normal stress because of axial loading, you have normal stress because of bending. These are three other stresses. Let's see the nature of these stresses. Let's first see the torque. Torsion or torque. The value of T max is 12,000 Newton millimeters. This is the stall torque. So this is the maximum. What is the minimum value? The minimum value is also the same. As long as you press your whatever, the tool or whatever it is against this, there is no fluctuation in torque. It remains at this torque. There are no highs and lows. So T min is also 12,000 Newton. So if we calculate Tm, mean component, it's very obvious. T max plus T min over 2, 12,000 plus 12,000 over 2 is 12,000 Newton millimeter. What about the amplitude component? T max minus T min over 2, 0. There is no, as long as you are pressing your tool against the sender, there is just one value of torque, and that is the mean torque. When you remove it, it becomes 0. There's no cyclic changes here. So this is the situation. What about the axial loading? Again, you have just seen that there's a load of 200 Newton. How is this load created? This is corresponding to this torque. You apply this Fn and the torque generates. As long as you are keeping your tool pressed, there's the same value of torque, and as long as you are applying this load, you have the same value of axial loading. There's no high value or low value here. There's no fluctuation in every cycle. So you can, again, using the same thinking, F max here will be minus 200 Newton. We just calculated. F min again minus 200. There's no fluctuation here, because the moment you remove the tool or whatever it is, there's 0. So your cycles of loading are when you, the time interval in which you have pressed your tool against it. At that time, you have the maximum value and that is the maximum value and that is the minimum value. There's no fluctuation there. So using the same very familiar expression, F max plus F min over 2 will give you minus 200 Newton, and amplitude component F max minus F min over 2 will give you 0. What about bending though? As long as you keep this pressed, there, because of Fn, Ft is generated, and because of these two moment arms, you have two axes on which you have moments, but you have calculated the resultant of these two moments already. So what happens is, when you apply this loading, as long as you are applying this loading, consider this point, there will be a bending moment. Because of bending moment, there will be a stress here, and this stress will keep its sign changing in every half cycle. After every half cycle, it becomes positive, negative, positive, negative. So what is the value of M max here? M max is the value you just calculated when you calculated the resultant. But what is the M min? That is minus of this, because the resultant value that you calculated, if this causes, for example, this causes a positive stress here, let's say, but after half a cycle it will become negative, and then it will become positive again. So in every cycle it is changing its sign. So this also has a negative side, negative sign with it, so that is this value. And if this is the case, then the mean value, m max plus m min over 2, this gives you 0 now. And amplitude component, m max minus m min over 2, that gives you. So if we summarize this, torsion has a mean component, axial loading has a mean component, and both these amplitude components are 0, because as long as you are pressing your tool against it, you have one value of torque and you have one value of compressive stress. But in case of bending, opposite is true. As long as you are keeping your tool pressed, in every cycle you are having a sinusoidal wave, and there will be an amplitude component of movement which is we have calculated, and the mean of that is 0, because you are having this kind of a situation, something like this, mean is 0. So if we have these in place, then the rest is very simple. Now we have to calculate using these stress constant factors, applying them on these, and we are going to calculate all the values, the shear stress values as well as the normal stress values. So for torsion, this 1.1, this is the kf for torsion into 12,000 tm into 8, this is the radius, this is torsion formula I am applying, over the value of j is pi by 2 8 power 4. Now what these values are, kf torsion, tm, this is the radius, and this value is the value of j, so this becomes this, and if you calculate this you have 16.4 MPa. If you use TA for the same, the amplitude component, because TA is 0, so tau A will be 0. Now we come to the axial loading. Axial loading is simply mean component minus 200, this is minus 200 over area by 8 square. This is your F mean component, and this is your area. This is minus 1.3 MPa, and your FA is, because FA is 0, if you put FA 0 here, you will get a value of amplitude component becomes 0. When it comes to bending, now the mean component should be 0, and amplitude component is, and let me write here, there should be 1.3 here also. This is the value of kf axial, this one. For bending component, axial component of bending stress, you have 1.2, this is the kf bending, into 20880.6 into 8 over pi by 4, 8 power 4. This one is MA, this one is radius, this one is radius, but this whole thing is I. And if you calculate this, if you simplify this becomes 62.3 MPa. So we have been able to calculate all these values, 6, 1, 2, 3, 4, 5, 6. Now this and this will give us one means stress for the mid-range component. This and this should give us the von Mises stress for the alternating component, the amplitude component. Now, when it comes to von Mises stresses, there's some discussion to be had before we actually go on and calculate that. And that discussion is this. The general expression for von Mises stress is very familiar one for 3D case in terms of principal stresses. This is sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 whole square over 2 1 over 2. This is a very familiar expression for you, should be. This is 512, equation 512 of your textbook in terms of principal stresses. This is the von Mises stress. Now, you may not always have principal stress values. Obviously, they can be calculated, but sometimes you already have values of stresses that are general values. So in that case, you have this expression, not sigma 1, sigma 2, sigma 3, but sigma x, sigma y, tau xy, etc. Again, this is under root. This is your equation 514. And this is again von Mises stress in terms of general stress components. Very familiar expression for mechanical engineers. Now, when there's plane stress, in plane stress you have sigma z is equal to 0 and tau zx is equal to tau yz is equal to, all these values are 0. You put these values 0 here, and then what you get is sigma x square minus sigma x sigma y plus sigma y square plus 3 tau xy square. This is your, again, expression for von Mises stress in case of plane stress situations. This is your equation 515 of your textbook. Now, can we further reduce this? Sometimes, as is the case we are considering at the moment, rotating shaft. In many cases, you have rotating shafts. It's a very familiar arrangement in mechanical engineering. And there's a common thing whenever there's a rotating shaft. What happens is something like this, as we are experiencing in this problem. What happens is this: you have this shaft, and there is a torque here. Because of torque, you have shear stresses. Let's talk about this element here. Because of this torque, you have a shear component like this on this element. And then you have, as we just saw, two axes of M. Okay, and this, let's call this my and mz, and in this plane you have this m value. But this my, this creates a normal stress in the x direction. If this is the x axis, sigma, this was tau. But this mz, this also creates a normal stress in the x direction. This one, both of. So if you combine them together, the net effect of this m is to have a stress in the x direction, sigma. And this torque, this creates a shear stress, because if you recall, on this here you have shear stress on this plane. But recalling the complementary property of shear, there will be a shear stress here also. So if I look at it from this direction, you have this situation: sigma tau. even if you consider the axial component, because there's an axial component also, force also, we have just seen, that also is in this x direction. So there's no sigma in the y direction. So if that is the case, and the problem that we are doing is exactly like that, and all shaft and bearing type problems where you have torsion and axial loading and bending loads, you have this type of situation. So luckily for us, we can further reduce this. Sigma then can be, because sigma y is also 0, you can simply write sigma x, we can dispense with x, plus 3 tau square. This is your situation. One means stress can be calculated as simply as this one. And this is not just for this question. All questions of this nature in which there's a shaft, there's a torsion load, there's a bending load, you can, obviously, if you calculated these values, you will have the same value, but we can dispense with these complicated calculations and we just can find out the one means stress by using this formula. And we are going to do that. We have these values and then we are going to apply, but we are going to apply this twice. One for one means stress amplitude component, one for the mid-range component. And let's do that without further ado. And the rest is very simple. First of all, let's write down the general form. This is the general form. And let's have these values handy with us. So sigma m prime will be this. The sigma for m, this is axial load minus 1.3, and there is no bending load mid-range bending stress. So this is just 1 minus 1.3 plus 3. As far as the tau is concerned, this is the mean mid-range, the mean value 16.4, because this one is 0, and because we are dealing with the m component, so this is simply this, and this turns out to be this. Sigma a, again the same expression, but for some amplitude component you have 0 here. This would have added with this, but you have 0 here, so only this 62.3 is needed. And if, this is an important point, if there was a value here, this is 0, if there was a non-zero value here, we would have divided it by 0.85, recall, because we apply that load factor for axial loading on the amplitude component, but this is 0, so no need for that. And as far as the amplitude component of tau is concerned, that is 0. So this is 62.3 MP. And if these values we have, then it's simply a matter of applying the yield the fatigue criterion. Let's apply the modified Goodman criterion. We were not told to apply a particular criterion, so it's our choice. The simplest one is this one. You can equally apply a Gerber. Putting in the values, recall that SE values we have calculated earlier, and those values are 306.4 and SUT value is 900. Sigma A 62.3. The rest is the same that we have been doing, and this means that NF is equal to 4.3, greater than 1, so you can say infinite life with this factor of safety in fatigue. Now there's a check for yield. Always a good practice to check yield stress, whether it is yielding or not, whether the question asks you or not. Now the important thing is to know that the sigma max that you are going to apply, you are going to compare the sigma max with the yield strength of the material, but this is not, you'll be tempted to add these two together, but that will give you an overestimation. Actually, sigma max value is, again, one means stress but calculated in this fashion. This will give you a different value. And you apply the load, these values, again you'll be using these values, and if you minus 1.3 here, sigma a bending, this one is sigma m, this is for axial loading mean, which is minus 1.3. Axial loading, this one is 0. Bending, in bending case, mean stress is 0 and axial one is this one. So you add all of them together, but we add the 62.3 with the minus sign because bending stress is alternating, plus minus plus minus. So minus, in one cycle they'll cancel each other, this will be positive and this will become lower, but on the other cycle, the reverse cycle, this will be this is always negative, this will be negative. So let's put the minus value here so that you have the maximum stress. Here this is simply, this one is 0, this is 16.4 square, and this is 69.7 MPa. The yield factor of safety is simply SY, yield strength, over, this is the maximum stress that can occur in this system. The yield strength 750 given in the problem statement, 69.7, this is 10.8. This may appear to be a very large factor of safety, but this is usual for fatigue problems because your design will be governed by this. This too may be a little large, but even if you keep it to a reasonable level, 2.5, something like that, this will still be very big. So if you see it in isolation, if you don't know this picture, you'll feel that this is a case of over design. But when you take care of fatigue, yielding, factor of safety becomes very large. If I draw this pictorially, then this is the situation. You have sigma m sm, sigma a sa, this is your se, sut, sy, sy. So this is, now you plot your values. Because your factor of safety in fatigue is smaller than in yield, it will cut somewhere along not here. So your effective failure envelope is this one. It won't pass here, it will pass somewhere around here. So your point plot somewhere, sigma a value is greater than this, somewhere around here. So this is your load line, and this is your sigma m prime, in this case sigma a prime. And while we are discussing this, I told you that this doesn't give you the maximum stress value. This is an overestimation, but sometimes it is used for a quick conservative check. Sometimes you can just add them together, and instead of using this is the more proper value, this is the proper way to do it. But if you add them together, you'll get a higher number than this, so it will give you a smaller factor of safety. And if you check it, if you just add them together, you'll see that your factor of safety in yield is 8.3. This is very conservative if you do it like this. But again, because this is governing, so it doesn't matter, this value doesn't matter that much. But if you are precise, you want to be precise, then you should use this expression. But sometimes in your textbook you'll see, for a quick conservative check, you can have this calculation also, because this does not involve this kind of a calculation. So that brings us to the end of this lecture. Thank you.